is like the third, fourth attempt at doing this, uh, doing this lesson again, or this continuation of what I started a long time ago. So in the first video, I presented the case when n is 1, when you have this curve, y equals x squared. You look at the symmetric normal lines. So you pick a particular x0 positive, and you form the normal lines through these two symmetric points. So at these two different points on the curve. So in the case when y equals x squared, it's nice. It doesn't quite flatten out as much at the origin. So you do get a minimum value as x0 approaches 0. But in the general case, when n is greater than 1, that doesn't happen. So I actually wrote up a bunch of this stuff, so I'll post it in the comments or wherever they post these things. So I'll post that, and then so I'll just kind of talk through it. So if you have a curve like this, y equals x to the 2n, you get your pick an x0, you form the tangents, and then you construct the normal lines off of those. So the equations of the two normal lines at these 2 points, at x0 and negative x0, are here and here. So you just use the point slope form. The slope of the normal line is the negative reciprocal of the slope of the tangent line. So you can do that. If you've been through calculus, then you can easily understand these things pretty well, I think. So you get these two curves, these two lines, and just solving this system of two equations and two unknowns, you can solve it. You find x is 0, so it intersects on the y-axis because of the nice symmetry. That's kind of what you would expect. And then the y-coordinate is given by this value right here. Okay, so you have your two lines. They always intersect somewhere on this axis. And what happens if x0 goes off to infinity, these two go out. The intersection point, the 2 points here and here go off to infinity, as well as the intersection point. That also goes off. But when you move closer to 0, so if you come in this way, then the intersection point actually hits a minimum value somewhere. And then as you get closer to the origin, it hits that minimum and then goes off to infinity. So it kind of shoots off again. But it does hit a minimum value. Okay, so we're looking at this intersection point, the y-coordinate of that intersection point, as a function of x0. Okay, so when you have a fixed x0, you get this picture, and you get a particular y-coordinate that depends on that x0 that you've chosen. Okay, so as x0 approaches 0 from the right, y goes off to infinity, it blows up, so you don't have that there. Okay, but it does have a minimum. This is a differentiable function in x0, and so you can take its derivative, and I just rewrote it here, just changing the 1 over x0 to 2n minus 2 to x0 2 minus 2n, just using properties of exponents there to rewrite it so you can differentiate it easily. So then differentiating using sum rule and power rule to differentiate that. And then find the critical points. So you know that the only real case that you have to look at is where it's 0. Where it's undefined, you kind of already identified that. It's not going to be defined at the origin, so you don't have to worry about that. But the point you're interested in is somewhere out here somewhere. So that's what we want to get. So we set it equal to 0, set the derivative equal to 0, and then multiply through by 2n x0 to the 2n minus 1. So what does that do? That clears the denominator over here, and it gets rid of the x0 to the 1 minus 2n here. So what you're left with when you multiply through by that, 0 equals 2 minus 2n plus, then over here, you're going to get 4n squared plus x0 to the 2n minus 2. Okay, so then from there, you can easily solve it, and you get your x0 is 2n minus 2 over 4n squared raised to the 1 over 4n minus 2 power. So this value is a location of a minimum value, which you can show. So if you took a second derivative, and I didn't write this part up, but you can kind of follow through it. So here's the first derivative. You take a second derivative of that. So then the power comes down again. So you get 2 minus 2n, 1 minus 2n. Since n is greater than 1, both of those are negative. So when you multiply the 2, it becomes positive. That's going to be positive since x0 is positive. And same thing over here. These two are positive. That's positive. The whole thing's positive as long as x0 is positive. So it's always going to be concave up. That's this, the curve y, which defines this intersection point. It's always concave up. And so that means that this has to be a minimum. Okay, the location of this critical point has got to be a minimum value, and the minimum value is given by this formula. Okay, so that's kind of what I was looking at here, and just kind of wanted to summarize it. So it's a neat, interesting symmetry property that maybe you haven't seen or thought of, and I just kind of thought of it, and I was like, oh, this is a pretty cool thing. So anyways, there it is, and we'll look at some other things. One is this also the location of the maximal curvature of the underlying curve? So that's another thing to maybe look at. But anyways, that's it for this video. Hopefully that'll be a little informative and get you excited a little bit about math. It's something that I really love. So this is my kind of thing. So enjoy, and I'll hopefully post some others soon.